Okay. We're going to start. Hopefully that quiz is okay. We're going to pick up with, we're still in 13.2. So I got the flu last week and I'm still recovering, so we're just going to relax. Everyone calm down. Like, no.
We've literally never been calm.
just calm down. Quiz today, like, everyone relax. No fast movements, no loud noises, no, now he's supposed to do that. No. I'm making fun of Anita, she's not even here. I'm going to have to do that again now when she shows up. Right? If you need to know something, I will tell you. Everyone just relax. Yeah.
Can you go over the quiz? It was really hard.
You found it difficult?
Yes.
Do you remember what version you had?
Can you just put the answers in?
Well, I'm going to put the answers anyway, but you won't see the work.
The first question had x equals t sine t.
Oh,
That's the B.
okay. So that's version B. It's very similar to version A. So yeah, I guess we can run through that very quickly. So I'll do that super quick. So quiz 3B. And it says, one will set up a line integral to find the length of the curve x equals t sine t, y equals t e to the t. T goes from 0 to 1. Well, we know that L is equal to what? General formula.
0 to 1 r prime of t.
I want the general formula.
The magnitude of the r prime of t dt.
Correct. Which we know that in this case that will flesh out as just x prime squared plus y prime.
Squared.
T. And so this is going to be 0 to 1. You're going to differentiate this.
So
So that's going to be
sine
t cosine t
squared
squared
and
plus
then less
e to the t plus t e to the t
Do we
squared
reflect it in that form?
dt.
wait, then do you need to simplify it or just this one?
Well, not much will actually simplify this.
Okay, so I get it.
It's okay to leave it.
Because it looks kind of ridiculous.
How was that defined? General formula. Yeah?
It would be the integral of r of t times the
Well,
magnitude
A to B, and what was it?
r of t,
It's f of r of t.
t and then the magnitude
Times
of
the magnitude
the r of t, r prime of t
R
dt.
prime.
Yeah.
You could write it that way. You could also plug in. You could also actually plug that in. Right, x of t, y of t times r of t. Either of those are fine. So that's A, B.
Wait, Professor,
Yes.
for the value a to b, can you put t initial to t final?
Yeah.
Okay, so I got it.
Because I didn't define what the start and end points are.
Okay, so I put t initial to final.
So this, the gradient, is just the partial derivative. Partial with respect to x, partial with respect to y, partial with respect to z. So 3. Now I gave you a function. And you needed to find
the partial
degree. So you just apply this formula to this function. So we take the partial derivative of this with respect to x. Hey, quiet down. Partial derivative of this with respect to x. This guy's just a constant, so it's just that guy. Partial derivative of that with respect to x is that, comma. Now you're going to take the partial derivative with respect to y. Oh, probably need a little more space, but let's actually do it. How do we do this one?
x over z,
X over z.
e to the y over z, and
Okay.
minus x squared z,
Comma, put the third component down here.
and negative x over z squared, e to the y over z, and minus x squared over, no, x squared y. Yeah.
I think I got that right. I think it's
So,
but I got it.
Yeah. Are we missing a y?
are we missing a y where?
It's negative xy over z squared.
Yeah, negative xy over z squared.
Yes.
Why?
Chain rule. The derivative of this is minus y over z squared.
Shouldn't the y be constant? So
Y
y
is
should.
constant.
Yeah, so it becomes
So what you have is y z to the minus 1. So if you differentiate that with respect to z, right, it just becomes minus y z to the minus 2, which is that. 4. So this was the a line integral with respect to arc length.
That will be
So we wanted to compute x, y, ds. C is the line from 3 to. Okay, so this is the one where you have to do really a lot of work for. So this is the one real problem on this quiz. So what do we do? What was the first thing we did? Parameterize. So you find your R of t, which is going to be in this case
3 minus t, and then 2 plus t,
t goes from 0 to 1.
0 to 1.
And so you can find your R
our penalty
Our
prime.
time of t will be
negative
1, right?
Right.
And then our
Which means that the
time of
magnitude
will be square root of 2,
just radical 2. There we go.
and then the integral of,
And then we're going to plug those in now.
yeah.
So we're going to, this gives us the integral from 0 to 1 because that's our limits here. I'm going to replace the x with this expression, the y with that expression.
3 minus t.
and 2 plus t,
Times the square root of 2.
Times that square root of 2.
and then dt.
And again, that's using the formula that I had you memorize earlier in the quiz, in the earlier problem. So that's radical 2. And from here, it's kind of like calc 1, basically. So you're going to expand out
6 minus
6
6t.
plus t minus t squared. Plus t squared over 2 minus and you plug in 1, so that's going to be 6 plus a half minus a third.
Did you have to reduce it more than that? Like, what's the policy? I'm just not sure.
Something like this, yes, I would go further. I mean, this time around, I guess I'll accept this, but if under normal circumstances, something like adding 2 or 3 fractions together, I take it all. Okay, so I have 6. This would be what? 1/6.
What's plus?
6 minus 2. And so what would that give us?
35 square root of 2 over 6.
37 over 6 times right. And the bonus was just writing down a formula, and which we're going to talk about today. So. Yes.
Is it a blasphemy that we change the orientation?
No, that's not a blasphemy. Blasphemies are very serious. They really go by what's written in the syllabus. So there are no new ones that are going to pop up for you guys. Okay, but that was basically the quiz.
Professor,
Yes.
can you do a homework problem just one about the vector field?
We didn't do vector field yet.
We did 13.1 vector field.
Oh, you mean to graph it? No, don't worry about it. Okay, so we're going to finish up 13.2. I actually wanted to do 2 more examples of guys like these. So I guess if you have trouble with it, you'll get some extra practice right now. And then we'll move on to line integrals over vector fields. So here's a couple examples to get us back into the groove of what we're doing. These are with respect to x and y. Here's C. It's the part of y equals x squared from 0, 0 to 2, 4. Just mention a couple things about the integral going the other way. 2, 4 to 0, 0. So this is not with respect to arc length, it's with respect to x and y. Just want to remind you guys how we do this. Well, how do we do this? What do we do here? Parameterize. So how would I parameterize? What would I set x to be here?
It could be x.
Yeah, t. We just call it a different name for no reason at all, actually. And what would you do your y?
T squared.
T squared. What would you say your limits for t are?
0 to.
And again, remember your x is t, so the limits just follow what the x coordinates are doing. So in this case, it's 0 to 2. And so, yeah, so now we can find our derivative here. Dx is just dt. dy is just 2t dt. And now we can just plug in. So this guy is just equal to the integral from 0 to 2. My y is t squared. My dx is just 1 plus x squared times my dy is 2t. And I can factor out the dt at the end. So this would just be 0 to 2, t squared plus 2t cubed. We'll get 2, you get 8 over 3 plus 8. No, it's not 48. 32. Okay. How would you change things if you wanted to go the other way? You can just take the negative of the answer, right? Note. to go from 0 to 4 to 0, 0, we could, one thing we could do is negate the answer. So that would just give us minus 32 over 3. Another thing we could do is we could have set up the integral, except we start the 2 down at the bottom and then put the 0 at the top, which is equivalent to negating the answer. But you can always, this is kind of probably the preferred method. You kind of set things up to have the orientation kind of built in for you whenever it's needed. So you kind of want to put the start point at the lower part of the integral and the end point at the upper part of the integral. Yes?
Question.
Mm-hmm.
For this problem, don't you need to find the magnitude of the R of t?
No, you only need the magnitude when you're doing the ds. Right? So,
Yes.
yeah, when we have, here we have dx, dy. You only do magnitude when you have ds.
Oh, okay.
Yeah. Which is why in the quizzes I always ask you guys the formula, because we're going to do many different kinds of integrals, and they're all found in different ways. You have to be really careful. Let's do another one. So we need some variety in our lives. Here my C is the line segment. From 1, 2, 3, 2, 3, 5, 7. So similarly here we're going to parameterize. So we'll just call our x something, our y something, our z something. What is x?
1 minus 2t.
Plus 2t. You're starting here and ending here. The y? 2 plus 3t. And the z? 3 plus 4t. So my dx is just 2 dt, my dy is just 3 dt. My dz is just 4 dt. Now I plug them in. It's 0 to 1 because I'm using that formula for the line segment. And so here my z is going to be 3 plus 4t times dx, which means I multiply by 2, plus my x is 1 plus 2t times dy, multiply by 3, plus my y is 2 plus 3t times my dz, just multiply by 4. Okay, so let's just go through the motions here. That'll be 6 plus 8t plus 3 plus 6t plus 8 plus 12t. Put these all together. 6 plus 3 is 9 plus 8 is 17. 8 plus 6 is 14. 12. That's 26, right? 17t plus 13t squared. See what we want. So that's just 17 plus 13. we're going to learn yet a different kind of integral, and it's kind of going to give you actually an interpretation for this kind of integral. So we've actually interpreted the ds integral before, and we could imagine it as the area of some sort of fence that's weaving its way through 3 space. But we never really had an interpretation for this. What does that 30 mean? We're actually going to discover that by looking at a new kind of integral.
Professor, what is the difference between the ds and the c versus c?
The ds and the what?
So you said that when you are integrating the c, you need the r prime of c, the magnitude of the r prime of c.
Yes, this guy here is equal to the integral from a to b of whatever the limit should be of f of r of t times the magnitude of r prime of t. This is a line integral with respect to arc length. Orientation does not matter, and that's the formula for calculating.
Okay.
If you have the integral of some function dx, then that's actually something different. That just becomes a to b. This is f of x of t, y of t, times x prime of t dt. Right? And of course, if you're adding them together, you can sum these together. And here, orientation does matter, so direction is important. And so these are 2 kinds of integrals we know so far. We're going to actually look at a third kind of integral, an integral that looks like this guy, which turns out is kind of going to be equivalent to a sum of these guys, and we'll talk about what that guy means. This guy is going to be, so this is a line integral with respect to arc length. This is a line integral with respect to x. You can also call it with respect to y or z or some other variable. This is called a line integral over a vector field. They all have their own formulas and their own interpretations. So let's talk about that last one. And we're not done with these integrals. We're going to be even talking about different kinds of integrals moving on. So actually knowing the definitions and knowing when orientation matters from when it doesn't is going to be very important. Okay. So if you paid attention to my notation, well, let me actually just write down the definition. I think that is it.
This is still 13.2.
Yeah, we're still in 13.2. So, definition. Let f of t be a continuous vector field. Right, vector field just means it's a function like what we described in 13.1. So it's a kind of something that describes the environment you're in. And let C be a smooth curve. Which we can parameterize by R of t for t between A and B. Then the line integral over f along C is defined by that integral, and its definition is the following. Let's go from A to B. F, you're going to plug in the parameterization again. Dot product with R prime. And so now I'm pronouncing this dot on purpose here, because it's not just regular multiplication, it's actually a dot product. And the notation is very deliberate. I'm writing arrows over things because I want you to think of them as vectors. And so it's not a regular multiplication that's happening here. It's actually the vector multiplication dot product. Technically it's called a scalar product or whatever. So this is called a line integral over a vector field. More specifically, over the vector field named f. Here's some remarks. One, suppose I describe f as, p, q, r, where these guys are functions, multivariable functions, and I can let my r of t be described as something like x of t, y of t, z of t. Then what you'll notice here is that I can think of my r prime as just the dx, dy, dt, dz. Which would mean if I start to set this integral up, what would it end up looking like if I dot product something like this with something like that? It's going to look like p dx plus q dy plus r dz. Right? And notice that that is just a line integral with respect to x, y, and z added together. Right? So you can actually think of these guys in the same way you think of the original integrals. So interpretation that we can put on these guys, we can now also put on the other integrals, the ones with respect to x, y, and z. So that's another.
Professor, don't erase this, please. 30 more seconds. Okay. Okay, done.
Another remark is the following. I'm doing some hand waving here because I'm not going to go too much into theory. But we spoke about that f describes the environment. Right? Which means it creates a vector field over your space. So at each point is assigned a vector, and it can have a certain direction and magnitude, and we can kind of think of these directions and magnitudes as having some kind of effect in the environment. So a vector will push something in a certain direction with a certain amount of force. And so we can think of it as describing the external force of the environment. Right? And that kind of means we can think of this guy as the integral of force along a certain path. And that means a very common interpretation for this guy. Who remembers what the integral of force is? Work. We can think of this as the work integral. This is the work to move a particle in this environment from point A to point B. under the influence of f. So one reason why we want to study this integral is that it tells us how a particle, neglecting other external forces that we can't actually account for, this sort of describes how much effort it will take to do something in a certain environment. Okay? And we can talk about, well, path is going to be important for us later on, but sometimes you want to move something from A to B and you want to do that in the most efficient way possible. And one of the ways to figure out what is the most efficient way possible is to actually study this integral. So it is an indication of how hard you will work to go from point A to point B in a certain environment. So that's kind of the interpretation. And since this guy can be interpreted that way, it kind of also means that this guy can also be interpreted that way. Right? They're kind of the same thing. So when we were doing these calculations over here, and we got values, we got 30, and we got 32 over 3, and all that stuff. It was kind of the work to move something under a vector field, under some sort of force field. Okay. So there are a lot of times when, well, let's actually do an example. So this is another typical kind of problem. One thing I want you to appreciate about this problem is it doesn't specifically tell you compute this integral, but it's kind of something you should know. Whenever I mention find the work done to do something, you should know I'm talking about the f dot dr integral. So that's something you should be aware of. Because that's a very core interpretation of this integral. So let's actually compute it. So let me actually just mention that. When you see that phrase, find the work done, or similar, this means you need to compute f dot dr. Okay, that's something you're supposed to know. Well, now you're going to know because I told you you need to. Am I supposed to? So that's a hint. Find the work done, you should immediately think, okay, this is the integral I need to compute. Okay. And let me just mention the process here. And again, like as I've been saying, because we're going to be doing so many different kinds of integrals, you really should have the process laid out for every kind of integral you have. Just like writing down the steps like I did with you the first time. So to compute that, the first thing you do is you find your R, meaning you need to parameterize. Find your dr, which really is just r prime. Then find your f of r of t, which means you just plug in your parameterization into the given vector field. The dot product. So you're going to take your f of r t, going to dot product with the r prime, and 5 integrate. Okay, so that's kind of the process that you think. So for example, I could ask you to compute this directly, but I could also ask you to find the work done to move along a certain path from point A to point B. You should then know that this is what you're going to do, and you should then know these are the steps I'm going to take. So let's actually go through that here. What is our R of t?
T, comma, t squared minus 1.
What are our limits?
Negative 2 to 1.
Negative 2 to 1. It's already in that order, so we're fine. So 2, now you're going to find your R prime. So that's going to be what? 1 comma 2 t. Third, now you're going to find your f of r of t. So what we have to do is we have to go where the f will be defined for you. They have to tell you what kind of environment you're in, or you'd have to know through some kind of research or analysis. So it's the y coordinate, which here I know is this. So it's t squared minus 1 comma the negative of the x coordinate, which in my parameterization is this, so that's just minus t. So now I'm going to dot product those and then integrate them. So it's this times that, t squared minus 1, plus this times that, minus 2t squared. Huh? What did you say? Okay. Maybe I should write that down just for emphasis so everyone knows where that comes from. So I'm going to integrate minus 2 to 1 of t squared minus 1 t dot product with 1 to t. But ordinarily you don't have to write that line down. I'm just doing it so that everyone sees what I'm doing. So that's just minus t squared plus minus t plus t cubed over 3 minus 2 and 1.
Is it minus t squared? You took it.
I took a minus
Oh, I
out.
didn't see that. Okay.
So plug in 1 minus, plug in a negative 2 say a minus 1 minus a third. This would be a plus 2 minus 2. This would be a plus 8 over 3 and then a minus 8 over 3. So this is minus 9 over 3, so that's just minus 3, and then minus another 3, minus 6, right? that would be the work done in moving our particle. I'll emphasize a couple things here. How we can interpret the negative answer is sort of like like energy is lost in the system. You can think of it as losing. The work would actually take away some of our resources here. Another thing you can realize is that I believe the guy y comma minus x is someone we drew before. That was the guy that was swirling like this. And we could actually look at that curve. I believe it was x squared minus 1. So we had the curve here. So we're in this environment where things are just swirling around the origin, but we're moving along this particular path. And we're moving along it from where our x is minus 2. So that would put us where? Give me the points.
Professor,
2, 3. Yes. Here.
Professor, how do you get the limit from -2 to 1? Like, I don't.
I gave you the points before. We're moving from -2 comma 3 to, I gave you the points, to 1 comma 0. And since
Okay.
my x was t,
Oh, x was, okay.
x is t, so my t values are following the x values.
Okay, okay.
Right, so I'm moving from this guy to this guy. And I'm actually traveling in this direction. Right? So how you can think of that is, I'm moving a particle here to there, but look at how what the environment is doing. When I'm going here, the environment is pushing against me, right? It's pushing against me the whole time. Like it's not helping me, it's actually impeding the work I'm doing. That's kind of why this answer is negative. I'm fighting the system in order to move in this direction. Yeah.
I was just going to say also the dot product, if you put a tangent on the curve against the force field, is negative.
Yeah. Yeah, so, but that's kind of the picture you would see in your head. You won't always want to draw this picture, but I just thought it would be cool to emphasize it here, what's kind of going on, and how you can think about a negative answer versus a positive answer. So you can think of a negative as kind of like, on average, it doesn't mean the whole time you're fighting the system, but it averages out so that you're fighting against the system more often than you're going with the system. So obviously if we're going the other way, the system would actually be pushing us. It would be helping us. We actually wouldn't really have to put in any energy to move the object. Right? The environment would have done it for us. And so in some sense here, it's better for us to go from this point to that point than it is to go from this point to that point. And we could actually figure that out by actually computing this integral. We can know in terms of degrees of difficulty how this can be, depending on the number that we get. Yeah, and that's the end of 13.2.
Could you do one more example?
Well, I only did one example.
We could do the other way.
That would just be silly. Just get a negative. one, it's kind of weird, but one of the last ones that we did, the two other. So you remember that we did this one.
Z, D, yeah.
Plus x dy plus y dz. It turns out we could have thought of this as f dot dr, where our f was actually the vector z comma x comma y. So that's the vector that's describing what's going on in our environment. Along the path. And R is line from 1, 2, 3, 3, 5, 7. So we could have done that. If this were a problem that you're given, oh, find the work done moved by this force field through that path, you could have done it here. And you would have gotten the same answer that we got when we did that at the beginning of class. So you could do something like first we parameterize our line segment, which would be 1 plus 2t, 2 plus 3t, 3 plus 4t. You can find your dr. It's going to be 2, 3, 4. You can find your f of rt, which is going to be the z coordinate, the x coordinate, and the y coordinate. And we know we're going from 0 to 1, and then we can dot product these. And what you've realized from doing that it's the fifth step. Now we're going to integrate 3 plus 4t times 2 plus 1 plus 2t times 3 plus 2 plus 3t times 4. You realize that's exactly the same integral we set up last time. It's actually a different notation. The next section is a super important section, but I'm not going to start in the last 5 minutes. But it's going to be, starting with the next section is when the really cool things are going to happen. So we'll end right there. I have quiz 2 to give back, so I'll give you guys that back and then we can move.